In this video, we're going to prove what has come to be known as Fermat's little theorem. It says if P is prime and P does not divide A, then A to the P minus 1 is always congruent to 1 mod P. And we're also going to prove a corollary to this theorem. If P is prime, then A to the P is congruent to A mod P for any integer A. If you notice, the one thing that's really missing for the if part is it doesn't say P does not divide A. Okay, so we will prove this after we prove the theorem. Why is that? Because corollary means consequence. This corollary is a consequence of the theorem. It follows from the theorem. So if we don't prove the theorem, then the corollary makes no sense. Okay, so the proof goes as follows. How about we consider the first P minus 1 multiples of A. The first P minus 1 multiples of A. 1 times A, that's the first one. 2 times A is the second one. 3 times A is the third one. This number in front is doing a perfect job at counting how many multiples of A that I am writing. And we want P minus 1 of them. Oh, so the P minus first one should be P minus 1 times A. Now, I claim that these are none of these two are congruent to one another mod P. Now, you can have only up to P minus 1 elements that are not congruent in mod P. You can only have up to P minus 1. In mod 7, 0 is not congruent to 1 mod 7, which is not, what I'm writing here does not imply that 0 is not congruent to 2 mod 7. What I'm basically saying is X mod 7, if X and Y are in the set 0, 1, 2, 3, 4, 5, 6, this is not congruent to Y mod 7, provided X is not Y. Okay, all these 7 are no pair of these 7 numbers are pairwise relatively prime in modulo 7. And that's what I'm going to show here, that I found P minus 1 elements that are, or numbers, where none of them are congruent to one another in mod P. Okay, so I make that claim. Let's actually say it as a claim. So just to make life easier, maybe I'll call it the set S. I claim that no 2 members of S, no 2 different members of S are congruent to one another. Are congruent to one another. Okay, I make a claim, I have to prove it. Suppose that R times A is congruent to S times A mod P. And say R is less than S. But all of them are between 1 and P minus 1. And I'm saying up front that R and S are not the same. And I'm going to get a contradiction. R and S are not the same. But, since P does not divide A, that implies that R times A is congruent to S times A mod P, that we can cancel out their A's. That is, R is congruent to S mod P. But what does that imply? That implies that P must divide the difference. But this can't be. For example, if we're in mod 8, so the only numbers that we're going to talk about are those 8 numbers. The biggest subtraction you can get is when you do the largest minus the smallest, which is 7. And that's less than 8. That's less than 8. And that's the largest difference. The smallest difference is if you subtract 2 consecutive ones. And that will give you 1. That is, this here, the subtraction is always between 1 and I can say less than or equal to 7. It's always between 1, the difference, and P. The difference is always between 1 up to and including P minus 1. Okay, well, this is less than P. But let me see one little thing. I said R was the smaller one, so let's live up to that. Let us write S minus P. S minus R. S minus R. But like I just argued, it's less than P. That's a contradiction. That implies that R is equal to S, which means that, where are we? It means that these two that we claimed were different were in fact the same. That is, they're not different. If R and S are the same, we're taking the same multiples of A. That is, RA is equal to SA. No mods, no anything. They're straight up equal. Okay, so what do we have? We have that these are N minus P minus A elements, and in mod P they're not equal. No two are equal. But you know what? There's another set. This is also true for the set T, which is 0 and 1 and 2 up to P minus 1. Okay, that means if I multiply, let's do the other one first. So 1A times 2A times 3A all the way up to P minus 1A, it must be congruent to 1 times 2 times 3 up to P minus A. No guarantee, the ordering may be different. That is, 1A might be congruent to 3, and 2A maybe is congruent to 1, and 3A is congruent to P minus 1. And P minus 1A is congruent to 2. But there's that pairing going on. And this is all happening in mod P. Okay, the left side, you have 1 times 2 times 3 up to P minus 1. Well, that's P minus 1 factorial times other stuff. Like A times A times A times A. How many A's? Oh, the number in front is telling us. That's the first A being multiplied. That's the second A. That's the third A. I'm multiplying A by itself P minus 1 times. This is the definition of exponents. And this is congruent to 1 times 2 times 3 up to P minus 1. Well, that's P minus 1 factorial mod P. Note that P does not divide P minus 1 factorial. You may say, well, why not? Well, why doesn't P go into 1 times 2 times 3 up to P minus 1? Well, this here is just 1 times P. You can kill off the 1, but all these numbers up here are less than P. Forget for one moment that P is a prime. The only way that P can go into the top, since all these numbers are less than P, is if maybe 2 times 7 is P. Like if you have 10 and you have 1 times 2 times 3 times 4 times 5 times 6. None of those numbers are 10 or 20 or 30. But 2 times 5 is 10. So you can kill off 2 times 5 and you're left with 72. 1 times 3 is 3, times 4 is 12. 12 times 6 is 72. But that type of cancellation can happen here. Okay? P doesn't go into any product on the top. Okay? Okay, so what that means is this last statement implies that keep in mind, you can always multiply by 1. That last statement implies that we can kill off P minus 1 factorial. That is, A to the P minus 1 is congruent to 1 mod P. Wow, Fermat was right. Well, I shouldn't say that. Fermat is always right. He's a brilliant person. I think it's an insult to call his theorem a little theorem. Fermat is God when it comes to the field of number theory. That completes the proof, mainly because I got the desired result. If you like seeing mathematical proofs done all the time, you should subscribe to my channel. But before we end this, how about we prove that corollary? Okay, so let's get rid of this proof and let's see what we need to do for the corollary. Usually corollaries, they're somewhat quicker proofs, because if they were more they're just consequences. They're direct result from, in this case, Fermat's little theorem. And this statement is up there for Fermat's little theorem. Okay, so proof. Now we know either P divides A or P does not divide A. Well, if P does divide A, then, and P is prime, then the conclusion is true. If P divides A, then the result, this result, is obvious. Why is that? Because if P divides A, that implies A is congruent to 0 mod P. Okay, so that means A to the P is also 0, because if I multiply 0 by itself, multiplying the left by A many times, but A is 0, and I multiply on the right by 0 P times, I'm going to get 0. But A is also congruent to 0. That is, I can say that A to the P is congruent to A mod P. Okay, so let me say this a little bit neater. This here, so we have this statement. It came from this. This implies that A to the P is congruent to 0 to the P mod P. But since this is 0, that implies A to the P is congruent to 0 mod P. Okay. Now, here's where it comes together. I have two things congruent to 0 mod P. This and that. If two things are congruent to the same, then these two things are congruent to one another. This implies that A to the P is congruent to A mod P. Zeros, this basically all that's happening is if P divides A, that means these are both zeros. And yes, 0 is congruent to 0 mod P. That's why I say it's obvious. But I gave a rigorous proof below. Probably many people would say it's overkill. So we did one case where P does divide A. Now, if P is prime and it does divide A, baba boom, we have this. That implies that A to the P minus 1 is congruent to A mod P. Congruent to 1 mod P. That's literally Fermat's little theorem. One of the things I said at the beginning was the only difference between this and this was that we didn't have that P divides A. But now we do have that P doesn't divide A. Here we have that P doesn't divide A. We weren't given that in the corollary, but in one of the cases we are. Okay, so Fermat's little theorem tells us this. But now we multiply both sides by A. Well, when you multiply this side by A, you get A to the P. When you multiply that by A, you get A. And in the second case, we got what we wanted. In both cases, what were the two cases? One case where P does divide A, and the second case where P doesn't divide A. There's only two possibilities. Either P goes into A evenly, like it did up here, or P does not go into A evenly, like it did in the second case. And in both cases, we came up with the same thing. In conclusion, we have A to the P is congruent to A modulo P. which is exactly what we wanted to show. That will complete the proof. If you just love seeing mathematical proofs like this, subscribe to my channel. See you guys in the next video. Thanks for your support. Watch and learn. Hit the subscribe button and the like link. Have a good day, guys. Thank you.